Okay, so today we are going to go backwards with some of the vector stuff that we talked about yesterday. Okay, so yesterday we had a vector where we knew each of the components and we figured out what the direction angle was. We figured out what the magnitude was. Okay, well, now what if we know the direction angle? What if we know the magnitude? Can we figure out the horizontal component and the vertical component? Yes? Okay. So we know that we would have to travel horizontally A and then vertically B in order to get our vector, right? So if I knew the magnitude and I knew the angle, how could I figure out A? No, wrong answer. Which trigonometric function? Okay, you guys are taking the ACT in like 2 weeks. We got to be quicker with this. What? If we have this guy and this guy. Cosine, because we have adjacent. Whoo, wake up, people, wake up. He was brave enough to actually answer for me. So none of you get to say, did you try? You were yelling out random things. We know that the cosine of theta is adjacent over hypotenuse. So if we wanted to know our horizontal component, we could multiply that magnitude over. So the magnitude of our vector times the cosine of theta would give us that horizontal component. Interesting. Let's try this again. What could I use to find our vertical component B? Sine. The sine of theta is B over the magnitude. Opposite over hypotenuse. Answer when I ask it. So B, if I multiply this over, would be the magnitude times the sine of theta. Okay, so we're just gonna like remember that happens, because no matter what vector we have in standard position, we're gonna be able to draw that picture. We're gonna be able to set up that same triangle, and the same thing's gonna be true. Okay, so what I want you to understand is that any vector can be broken up like this. The horizontal component is magnitude times cosine theta. The vertical component, magnitude times sine theta. Okay, so here, I'll have you write it in component form first, and then I'll have you write it in linear combination form. Okay, and then if you want it in linear combination form. Yes, you want I first and then J, because I is the horizontal component that needs to come first. I don't know if I specified it. You basically just admitted that you don't always pay attention.
That's
Okay. You're not the only one, especially on a day like today. All right, we can focus. We can focus for a few minutes. Here we go. I want to know the component form of B if the magnitude is 2 and our direction angle is 45 degrees. So go ahead and write down this given information. We'll work through this together. Grayson brings up a wonderful question. Do we get to use a calculator? Technically, yes, you will get a calculator on your test. However, if you are given a special angle, is 45 degrees a special angle?
Yeah.
Yes, if you're giving a special angle, I want you to give it to me in exact values. Okay. What's a special angle? Something from the unit circle. Okay. 150 degrees, 240, 300. 45 degrees, whatever. If it's a unit circle angle, I'd like you to use that knowledge, even though the calculator would technically be in your hand. Okay. So, vector V. We know that the horizontal component is going to be magnitude times the cosine of theta. And our vertical component is going to be magnitude times the sine of theta. Not that I know how to do. Mm-hmm.
Is there a difference between the V with the lines and the lines?
With the lines is magnitude. And what's what?
The one without it.
That's just the name of the vector. All right, so what is the cosine of 45 degrees? What did you say? Radical 2 over 2 times 2 would give us radical 2. Okay, now this 45-degree angle is in the first quadrant, is our vector in the first quadrant. Okay, that's good. If it wasn't, we'd have a problem. Okay, those are some ways to kind of process through. Does my answer make sense? Okay, all right, that one wasn't so bad. Go ahead and write this example down. I want to know the component form if our magnitude is 3 and it's in the same direction as this guy right here. Okay, Patton just asked for clarification. Same direction, does that mean same angle? What would you say? Is that what you were thinking? Questioning also? Okay, yes. So basically, I gave you a different vector, but I want the same direction angle, okay? Which means what are we gonna have to do with this? Find the direction angle, all right? So we need to take the tangent of theta equals B over A, figure out what this angle is. Okay, now which quadrant is this vector in right here that we're finding the direction of? Quadrant 3. Okay, so in your calculators, when you take the inverse tangent of 4/3, you're probably going to get an acute angle. We need to take that reference angle and make sure we get a third quadrant angle. So in your calculators, please take the inverse tangent of 4/3 and then do what you need to with it. Check in with your neighbor, make sure you're all 4 getting the same thing. We're all here today. This is so great.
Yeah, I got that.
But then we change it to one.
So that would be if it was in the second quadrant.
Oh, yeah.
But still,
Third quadrant would be more than 180.
wait, what's
Oh.
So 233.1.
Oh, so it's 360.
No, you add 180.
Oh. Wait. So you did that.
Correct.
Okay.
So 233.13. Okay, so your acute angle was 53 degrees, 0.13. But then we're gonna have to add that to 180 to get our third quadrant angle. So now I want our vector. Okay. Our vector is going to be magnitude times the cosine of our angle, I, plus magnitude times the sine of our angle, J. Well, what? But you're only gonna punch in like the coefficient for I first, the horizontal component first, and the vertical component separately. Okay, now we're going in the same direction as that -3i minus 4j. So we're probably going to get a third quadrant vector. Okay, what happens when we take 3 cosine of 233.13? What about this one? There we go. All right, can we do that? Yeah, yeah, we can do that. We can do that. All right, now let's work with two vectors. I have vector u and vector v, and I want to find the sum of vector u and vector v. So first of all, I need you to write down the given information. That way, when you look back at your notes, you know what the heck is going on. Now you don't have that.
No, I know.
Okay, if we want to add these two vectors together, can we do it right now with that information? Okay. Yesterday, when we added vectors, we added the vertical components together. We added the horizontal components together, probably in the reverse order, but whatever. Okay. Which means we're going to actually need the separate components of each vector so that we can add them together. All right. So vector u. Vector u has a magnitude of 4.5 and an angle of 60 degrees. So we're going to take magnitude times the cosine of our angle for our horizontal component and magnitude times the sine of our. You're mumbling, what? Why is the theta there? Yes. Yes. So this is the angle for this guy. This is the angle for this guy. Okay, I don't really like that these are decimals because cosine of 60 and sine of 60 are going to get us fractions. So what's 4.5 as a fraction? 9/2. Okay. Gotcha. What is the cosine of 60?
1/2.
We have 9/4. And then the sine of 60 is radical 3/2. So there is vector u. Okay, now let's talk about vector v. Vector v has a magnitude of 5 and an angle of 90 degrees, which I'm pretty excited about. Okay, so we have magnitude times the cosine of 90, our horizontal component. Magnitude times the sine of 90 for our vertical component. Cosine of 90. Oh, Isaac was ready for that one. Cosine of 90 is 0. Sine of 90 is 1. Okay. So now we get to add these two vectors together. Okay. So our two vectors, when we add the horizontal components, we would get 9/4, lame. Okay. Not lame, actually kind of nice. And then when we add our two vertical components, we can't actually combine, bless you, those together because one is irrational and the other is not. So we'll just leave it like this. I mean, if you wanted to write it as 20 plus 9 radical 3/4, that's fine, but it wouldn't be necessary in this case. All right, how many of you have taken physics or are in physics of some kind? Really? Okay, we're being a little bit hesitant with our hands there. Our next two examples have more of a physics feel to them. Okay, it's kind of nice when math and science overlap. Okay, and you see some familiar problems. Here's what's happening. We have a force of 2,000 newtons and 900 newtons. Look, I even used newtons this time instead of like foot-pounds. Oh yeah, we'll get there. So these forces act on a machine part at angles of 30 and -45 respectively with the x-axis. Find the direction and magnitude of the resultant of these forces. Ooh, resultant, that was a word from yesterday. We need to add these two vectors together that are acting on their machine part, and with the resultant, with the sum, we need to find the direction and magnitude. So I want you to take 30 seconds and just jot down that 2,000 newtons is the magnitude that goes with an angle of 30 degrees. 900 newtons is the magnitude that goes with the angle of -45 degrees. I was thinking ahead. Okay, so just like in our previous example, if we are going to add these two vectors together, we need them in their component forms. Okay, so I'm just going to call this vector u, is gonna be our red vector. Our red vector has a magnitude of 2000 and an angle of 30 degrees. Okay. Now, as we're writing this down, okay, someone mentioned earlier about physics. The magnitude of vectors are sometimes a force, okay, which is what's happening here. If we have a force acting, that is the magnitude of our vector. Okay. All right, so we just talked about the cosine of 60 being 1/2. That means the cosine of 30 is radical 3/2. And the sine of 30 is 1/2. Why is it what? Well, our vector u has a consistent magnitude. The magnitude has to be the same for both components. Now we're going to go to our second vector that has a magnitude of 900 and an angle of -45 degrees. Now we know that the sine and cosine of 45 degrees is both radical 2/2, but when we're -45, one of them is going to be negative. Which one? Yes, because we're in the fourth quadrant. Okay. So we have radical 2/2 times 900 would give us 450 radical 2, and negative radical 2/2 times 900 would just give us negative. Okay, so when we add our two vectors together, we're adding 1000 radical 3 plus 450 radical 2 for our horizontal component. And then we're adding 1000 plus -450 radical 2 for our vertical component. Okay, those aren't nice numbers. And we're going to have to find the direction and magnitude of these guys. Okay, so I want to help you be efficient with your calculator, so I want to show you a trick. Can I show you a trick? Okay, so if you don't have your calculator out already, please have it out so I can show you this trick. Okay, I'm going to show you the store feature in your calculator. Maybe I have already, but if you forgot about it, then I'm just going to reteach you. Okay, so I'm going to call the horizontal component A and the vertical component B. And when I go into my calculator, this is what I'm going to do. So our horizontal component, come on calculator, is, what was it? 1000 radical 3 plus 450. Oh, shoot. I'll get there. Plus 450 radical 2. Go ahead and hit enter. Do you get 2,368, blah, 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 blah. This is what I'm going to have you do. You see this button right here? It says STO. That's the store button. We're going to store this in alpha A. So anytime I bring up alpha A, it's going to be that number. Okay. Then I'm going to type in my second, my vertical component, 1000 minus 450 radical 2. Okay, and that's going to be 363, blah, 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 blah. And I'm going to store it. So press store in alpha B. And anytime I hit alpha B, that number is going to be in there. Okay. gonna make our life a little bit easier now, because we need to find the direction angle. So I need, until you overwrite it. Okay, so we know that the tangent of theta equals b over a. So in my calculator, I'm going to take the inverse tangent of alpha b divided by alpha a. Oh, I'm in radians. Do you get 8.7? Okay, that was a lot easier than having to put all those numbers in, right? Okay, we know that the magnitude of our vector is the square root of a squared plus b squared. So in our calculator, we can take the square root of alpha a squared plus alpha b squared. Boom. And we don't have to worry about typing all of those crazy long decimals in. Okay. Okay. Now, if the label of our magnitudes was newtons in our problem, then when we add the two forces together, they would have a magnitude also labeled in newtons. So I put N for newtons. Is that acceptable, physics peeps? Now, you're welcome to write out these numbers in decimal approximation form and punch them into your calculator, but I bet we just saved ourselves about 2-3 minutes. Okay. And I want you to kind of know how to work your calculator a little bit. All right, one more problem. Are you ready? Yeah. Okay. Wake up. All right. A gun with a muzzle velocity of 1,200 feet per second. I know you love that speed, feet per second. Is fired at an angle of 6 degrees with the horizontal. I want to know the horizontal and vertical components of velocity. Okay. So in this case, we have a vector whose magnitude is 1,200 feet per second, and its angle is 6 degrees. I want to know what the horizontal and vertical components are for this vector. Okay. So, I mean, this is just what we've been doing, right? Our horizontal component is just going to be 1,200 times the cosine of 6 degrees. $1,193.43. Is that right? Reading upside down on next calculator. Okay. And since our vector has a magnitude that we labeled in feet per second, so will the horizontal component. Okay, so what does this mean? If you were to like lie on the floor underneath and watch the bullet fly by, you would have you would only have the perspective of the horizontal movement. Do you see what I'm saying? If you're lying on the ground, you could only see the horizontal movement. You wouldn't be able to tell how high it is. So you would see that bullet flying at 1,193 feet per second. Okay. If there was a bulletproof wall right here that was see-through, and you were watching the bullet come straight at you, you wouldn't really have the horizontal perception. You'd only have the vertical perception. And the speed as that bullet is rising is going to be, oops, oh, I did not write. Is going to be 125.43. Okay, that bullet is changing vertically at 125 feet per second. That bullet is changing horizontally at 1,100 feet per second. Okay, that's what those two different parts mean. Okay, something I will expect of you on Friday is to write these separately with labels. The horizontal component is 1,103 feet per second. The vertical component is 125.43 feet per second. Okay, so make sure you have those labeled. All right, so you notice that we had a couple application problems in here. That doesn't mean when you see words, you just like don't try the problem or you skip the problem. These really aren't that bad. Okay, so I need you to attempt your homework in its entirety. But I won't see you until Thursday. So you decide when you need to do your homework. Okay? Honestly, I would stick in the routine of doing it the day that it gets assigned, just so you don't like pile up your work for tomorrow. But you do you.